There are two things that we need to know. And this is easier than understanding three-dimensional torques. Everything's going to be coplanar. So we've seen these equations before. The other thing I just want to say again is this is how angular momentum relates to eccentricity. You have more angular momentum, you're more circular. And the second one that I haven't emphasized before is that orbits precess because they feel the mass of other bodies nearby. And circular orbits will precess faster than eccentric orbits if they have the same energy or semi-major axis. You can plot this numerically, you can talk about the length of an eccentricity vector, speed of precession versus eccentricity, or you can think again of boats. So in this case, we have a kayak. If you've got a really short kayak or a small eccentricity, because the eccentricity vector relates to your eccentricity, it's really easy to turn around. But if you're in like a kilometer-long kayak and you have to suddenly turn around, it's going to be really hard, right? So this is the intuitive explanation for eccentric orbits take a really, really, really long time to turn for the same amount of forces nearby. If you're more circular, you go more quickly. Okay, and with that, why are the disks stable? So what I'm drawing here is a schematic. This black line here is meant to represent the entire eccentric disk around the black hole, and I'm just perturbing one orbit ahead of the disk. This is the direction of precession. So what's going to happen in this one orbit? Well, we go back to our equations again. Its angular momentum vector, r cross v, means it's pointed upwards this way. The force it feels, though, is going to be back in this direction. So the force is going to be acting against its velocity vector. So the torque, or the rate of change of angular momentum, is going to be negative. So it's going to get more eccentric. So if you get more eccentric, it's really hard to precess. And so you slow down, you get more and more and more and more eccentric because of the torques from the disk. And the disk keeps precessing, and the disk catches up to you. Now you can then fall off the other side of the disk. What if you're too eccentric and you just slow down to a complete halt and the disk just keeps precessing away from you? Well, the torques reverse. So here, your r cross v, the force is now in the same direction as your velocity vector at apocenter. So your torque is positive, your angular momentum increases, you get more circular. It's easier to precess as a circular boat, so you catch up to the disk. So you just oscillate back and forward across the disk and you're stable. So it's just differential prograde precession is really important. I'm not going to go into that, but you need to be prograde in your precession, and gravitational torques. That's all you need, and your disk is stable. So you can show this in n-body simulations, and I have a couple of slides that I've thankfully skipped because we're running out of time. Where am I going with this? So the disk, even if you started off with a flat eccentricity distribution as a function of its radius or semi-major axis, the disk wants to tilt in its eccentricity gradient so that the inner edge is more eccentric than the outer edge. This is seen in the Andromeda nucleus and wasn't explained before. We can explain it with torques and precession really easily, which I won't because I've got to move on. But why this is interesting is that your inner edge becomes very highly eccentric. And then orbits at the inner edge oscillate. So you can oscillate at a really high eccentricity, and when you oscillate to really high eccentricities, you're in danger of interacting with a black hole as you go around your pericenter position. So this is just from one of our simulations. This is 1 minus eccentricity, so you're increasing in eccentricity as you go down here. If you get to 10 to the minus 4 in 1 minus eccentricity in the simulation, you cross the tidal disruption radius of the black hole. So you can see this happens very frequently in our simulation. This was quite a surprise. I hadn't realized this would actually pop out. This is from James Gearshan, who's recently here. Tidal disruption events, I think everybody's very familiar with. We don't need to go into it too much. But you get ripped apart by the tidal forces of the black hole. If you get too close to the black hole, a lot of the material will subsequently accrete and form a luminous flare. And so we can see these tidal disruption events happen in external galaxies. And this field is kind of taking off in recent years. And so we have some really interesting observational data now about where do we see these tidal disruption events happening? Could they be correlated with eccentric nuclear disks? Okay, so in my model here of like eccentric nuclear disks, they're stable, they might be in lots of different galaxies, and they produce tidal disruption events. I need to answer the question, where therefore would we expect to see most of the tidal disruption events? So that goes back to the question of like, well, how do you form the disk in Andromeda? How do you form eccentric nuclear disks at all? And so I refer to Phil Hopkins and Elliot Quattart for this. They showed that when you merge gas-rich galaxies in a major merger, so the black holes are a similar size, the torques that are exerted on gas in the galaxy forces gas on low angular momentum orbits to the center of the potential. You can actually form a highly eccentric accretion disk around the black hole. Now, depending on star formation prescriptions, you can then collapse that gas or fragment that gas and form stars and just form your eccentric nuclear disk like this. So it's one way to do it, and I like it because it fits in with the story I tell myself. So you've got some galaxies, you've got a bigger galaxies, magic, you've formed an eccentric nuclear disk at the center. Now what? Your TDE rate at the point of where you formed this disk is going to be extremely high. You notice I don't have any numbers here, and that's for a reason. I don't know exactly what it will be because n-body simulations are not a good way to do this. But the rates I derive from looking at my simulations and matching it to some other stuff are so high that you can get one per year, right? So if you throw a star into a black hole at a rate of one per year, I don't know what that looks like, but I imagine it's a mess, right? So it's just gassy AGN. You're not going to see a very nice tidal disruption flare that you can pick out easily. And it's also the early stages of a galaxy that's still relaxing. There's a lot of dust around. But let me move on because I have 3 minutes, no questions, we'll be fine. I'm going to keep going. As you pump more and more stars into the black hole, you decrease the mass of the disk, but all those stars had extremely low angular momentum. So you've donated all that stellar orbital angular momentum to the disk before you fired yourself into the black hole and you got rid of some mass. So your disk grows in angular momentum per unit mass, so it will drop in its eccentricity slowly over time. Now the disk will still remain stable, but will become harder and harder with time to actually keep throwing stars into the black hole because your average eccentricity is dropping. You could go through a phase where it looks like a quasar and AGN, but then all of a sudden you've got a TDE on top of it. But once you reach a stage where you're like 1 billion years post-merger, maybe you'll reach a TDE rate that's allowing you to individually see the TDEs at this point. You have a star being tidally disrupted, the black hole eats it, and then you've got to, you can wait for a while until the next one goes in. Okay, I'm aware I'm running out of time. What's the observational evidence, if any? So this is extremely controversial, but the next one isn't, so hold on. So Tad Hunter in 2017 had a paper where they were looking at Euler galaxies, so these are ultraluminous infrared galaxies, thought to be kind of the peak phase of a gas-rich major merger. And they were looking at 10 of these Eulers, and they found a TDE candidate in 1. So you'll notice where the rate comes from. All right. So it could be extremely high if this is indeed a tidal disruption event candidate. It was weird, it plateaued, it's been going for like 10 years, but that's okay because in this model we're saying you don't just fire one star in, you keep going. And it's going to be a mess, you're not going to be able to see the luminosity profile drop off as you might theoretically expect. But by far the more robust evidence by Yera Kavi in 2014 and continuing is that the TDE rate in K+A galaxies, these post-starburst, probably post-merger galaxies, is really highly elevated, but less than this TDE rate in Eulers, something about once every 1,000 years. And to give you some idea, in a background sample of galaxies, like normal galaxies that aren't recently merged, we expect that rate to be something like more like 1 every 10,000 years, or 1 every 10 to the 5, 10 to the 6 years. So this is the drop-off is suggestive, I would say. So some predictions from this work is, of course, your recently merged galaxies should host eccentric nuclear disks. We could talk about this for a long time. The problem is there's not that many close to us, so it's really hard to actually find them and resolve their nuclei to be like there is an eccentric nuclear disk like Andromeda. We don't have a lot of time. You can ask me afterwards about the effects of mass aggregation in these disks. This is something we've just started looking at, and it's way more interesting than we realized at first. Just thought, mass aggregation, everything's move in. That's cool. It's way more interesting. I won't go through these. I did want to show my grad student Heather's work, so I'll just focus on this plot here, which is that if you do have a really high event rate of tidal disruption of events, if you were just in a ball around the black hole, some like ball of stars like in our own galactic center, you would not expect any correlation between the orbital properties at all from one consecutive TDE to the next. But because these are all coming from this eccentric nuclear disk that has a midplane, what we found is that one TDE to the next does show interesting correlated orbital properties. And in particular, there's lots more stars that want to tidally disrupt at 0 inclination or 180 degrees inclination. They actually flip back and forth in the disk in an interesting manner. So this could be interesting because your angular momentum vectors can be aligned or completely misaligned in 2 consecutive events. Okay, I think you can read them here. I guess the top one is something that I'm really interested in, but it's not something I specialize in at all, so I'd be interested to chat to people. What is the difference between a whole bunch of TDEs and an active galactic nucleus?